Hello, AS Math. It's Mr. Knight yet again, and we're on the final stretch of the first quarter, and we're going to continue on with what we ended with last week, which is looking at progressions. Now, we looked at arithmetic progressions. There's also another type of progression, geometric progressions, which we're going to talk about shortly. Here are our skills today, and then we got a little bit of vocab. And guys, I gotta be honest with you. Rick, my brother, is actually looking for a job. I know, he's been out of work for so long, and he somehow landed quite an amazing opportunity. But he's trying to choose between two jobs. So, I know, it's crazy. I don't know how he got them either. But he got those jobs, and here are his two jobs. Okay, job one. I don't know how he landed these jobs. Job one pays him $500,000 a month. Every month he's getting $500,000. That seems pretty tempting. Job two seems a little less tempting. It only pays him 1 cent per month. However, after every month, his salary will double. So he's going to kind of be living life on the edge, paycheck to paycheck. At least for a while until that thing starts to double. So it's up to us. I want you guys to think, and if you're in class, especially we're going to do this, I want you to decide and talk amongst yourselves which job should Rick pick. And if you're at home, go ahead, pause the video, and give it a little bit of a thought. And go. Alright. Well, I think there's only one way to figure this out, and that is to figure out something about job two, because job two is actually a geometric progression, which we're going to look at a little bit more. So let's work our way towards that. So first of all, a geometric progression. Here is a definition that you can now see. It is a geometric sequence is a sequence in which one term is multiplied by a fixed amount every single time. So similar to arithmetic progressions, how they have the common difference, and you add and subtract that. This one is a common ratio, and it's actually being multiplied by each term over and over and over again, okay? So for example, if I have 3, 6, 12, 24, 48, this is definitely not an arithmetic progression. We are not adding, we are multiplying by a fixed amount every single time. So here is some notation when it comes to working geometric progressions. It's kind of similar to arithmetic. First term is a, number of terms is n. Now this time our common ratio is going to be an r, and then our general term is going to be a mu sub n. So if we're looking at this, we know our first term is 3, we know we have 5 terms, and now we got to figure out what our r is. Now looking at it, you can see, hey, we're multiplying by 2 every single time. So that has to be what our common ratio is. But let's say it was a little bit more complicated and we really didn't know. It was kind of hard to tell. If you ever want to find your common ratio, you divide one of your terms by the previous term. So for example, I picked 12 and I'm going to divide by the previous term of 6. 12 divided by 6 will give me 2. And so we're multiplying by 2 every single time. That is the mathematical way to actually find that, which is quite useful. So moving forward, let's kind of look how this sequence is being generated. Let's look at the pattern, okay? So I'm going to use same color. If we're starting with u sub 1, we know that equals a, and that's 3. U sub 2 is, we're going to multiply my starting amount by my common ratio. So 3 times 2 is 6. Well, in order to get to the next one, I actually need to multiply by the common ratio, but the common ratio this time is going to be squared this time. So this time it's going to be by 2 squared, which is 4 times 3, which equals 12. And sweet, now we have a good pattern to work with. The next one is just going to be r to the third, which is 2/3, which equals 8. And 8 times 3 is 24, and now we're cooking. Now you can see kind of how the pattern is going. Now, noticing this, right? we're in the 5th term, but my common ratio is only going to the 4th power. So it's whatever this is minus 1 to give us that exponent, and then we multiply that common ratio exponential by our starting amount. So if we were to continue this forever, we would end up with these two guys right here. This is u sub k equals our starting amount times the common ratio raised to the k minus 1 power. So whatever term we're trying to find. If you want to find the last term, your n is going to be your number of terms, and that replaces your k in both sides of the equation. So now let's actually see how to find the nth term of anything using these two equations, right? These are going to be really the only two equations that we need for today. So let's use them and get some practice with them. Skill 1, finding the nth term. We want to find the 7th term in the geometric sequence 8, 24, 72, 216. Well, we know what our a is. Our a is just going to be 8. Our r can be found by dividing one term by the previous. So if I do 24 divided by 8, I will get 3. And we want number of terms to be 7. So now if we put this all together, we get mu sub 7 equals 8 times, we're going to do 3 to the 7 minus 1 power, which is 6. And guys, I'm going to be honest with you, I highly recommend using a calculator, really for arithmetic, but especially geometric. You're going to see these guys get huge very quickly. So how do we type it in? Well, we got to do our order of operations. So I do my exponent first, 3 to the 6th power, 729, and then multiply that by our starting amount of 8. We get 5,832. And that climbed really fast. That's only the 7th term in this sequence. But we didn't have to spend all that time trying to find it. We have a nice handy-dandy formula to do that. Okay? So let's move forward now. Let's look at our second skill. This is finding the number of terms in a sequence. And it looks like my marker just kind of like bled through and kind of gave us a cool looking design, but we're going to work with that regardless. How many terms are in the geometric sequence 4, 12, 36, 708,588? That escalated quickly. All right. But let's see what we know. We know what our a is. Our a is just going to be 4. We know what our common ratio is going to be. We could just do 12 divided by 4 and get 3. And now, well, we're trying to find the number of terms. So, don't know what that is. But we do know what the last term is. Mu sub n is just going to equal this big guy right here. Okay, so if we're plugging all that stuff in, let's just kind of replace what we got. And that's going to equal 4 times 3 to the n minus 1. Now we're solving for n. So what we could do right off the bat is we could divide both sides by 4. And we're going to be left with, I'm going to divide that by 4 because I have no idea what that is. There actually is a mathematician out there that can actually solve that stuff just by looking at it. We'll watch him maybe one day. He's kind of a weird guy, but I guess, you know, if he likes math, he's already weird to begin with. I mean, take it from me. So now we're left with this. Now, there is a mathematical way to do it, and we're going to look at that in a little bit. However, whenever you're presented with something like this, there's really two ways to go about it. First way we're going to do it is the way that I don't like doing it because it's not mathematical, is just by looking at it, which I know I've discouraged a couple of you in the past from doing that, but we're just going to have to look at it for a second and try. So what you could do is you could take your 3 and you could start raising it to powers until you get there. So if you try 3 to the 9, not quite. Let's try 3 to the 11. Hey, there it is. 3 to the 11 actually works, right? That's cool. All right, 3 to the 11. So I know that n minus 1 is going to just equal 11. So now all I have to do to solve for n is add 1 to both sides, and I get n equals 12. There are 12 terms in this sequence. Who would have thought? Now, here's a more mathematical approach. We are not going to learn these too much, if at all. This is really the only time you will see these in this course, and that's logarithms. If you've never used logarithms before, we're going to do a very quick review over them, okay? And if you've never seen them before, I guess it's not a review, it's just kind of seeing it. Because I'll show you a trick to use with them. First of all, if I'm given something like this, 4 to the x power equals 16, we can use logarithms to solve exponentials like this, to solve for x. There's nothing other than a logarithm that can really help us. And looking at this, you could probably guess that x has to equal 2. Now, what this does is we take this guy and we rewrite it like this. We do log base 4, because this is our base, of whatever's over here, 16, and then that equals the exponential. If you type this into your calculator with log base 4 of 16, just take my word for it for a second, you will get 2 equals x. You have to use a calculator in this case. Obnoxious, I know, but it is what we got. But what I want to look at is something you could do with logarithms. Now, let's pretend again I have 4x equals 16. What I can do to both sides is I can take the log of both sides. In this case, I'm using log base 4. I don't have to, but I'm going to illustrate it. What happens is this exponent here, because I took the log of it, can actually come out in front of the logarithm. Like this. What ends up happening is log base 4 of 4 will cancel out to 1, oddly enough, and then we're left with x equals log base 4 of 16, and then x equals 2. Nice. But this trick that I just showed where you could take the x and put it out in front if you take the log of both sides is what I want to focus on. So, if I have 3 to the n minus 1 equals that gross looking thing, I can actually take the log of both sides. And if I take the log, you might notice I don't have a base. I don't have base 4 or base 3. If there's no base stated, it's implied it's log base 10. Okay? So if I take the log base 10 of both sides, I can move this n minus 1 power out in front. Then I can treat it like its own quantity. And I can divide both sides by log base 3. And so n minus 1 is going to equal this stuff. So how do you put that in a calculator? Since we're using TI-84s mostly, your log button's right here. And I'm going to do log of 177147. Close it off. Divided by log of just 3. And I get 11. Why? Just take my word for it, okay? We get 11 out of that. N minus 1 equals 11. Add 1 to both sides, you get n equals 12. That's an alternative way to solve it using logarithms. I encourage you to try to do that just to get more practice with logarithms. But yeah, that's the mathematical way of doing it. Kind of weird, I know. So that brings us back to Rick. Good old Rick. Let's check it out. So which job should Rick actually pick? Job 1 was arithmetic, okay? And we're going to do this after 2 years or 24 months because we are going by a month every single time. So if I use this equation right here for my arithmetic progressions, I substitute 500,000 in for A and my common difference because it's both. 24 minus 1 is 23. Throw that into a calculator. He's going to make $12 million, which grinds my gears, man. I don't think I'll ever make that in my lifetime, but Rick's got special skills. I told you, man, he can throw a football over the wall of ice. I'm telling you, and he's showing you up. But here's job 2, geometric now. Let's say my A is 1 cent. My common ratio is going to be 2. That makes sense because it's doubling every year. And I'm going for 24 months. I throw that into the equation for geometric progressions. I throw it in my calculator, and I only get, 83,886. $1,000,000.08, which seems like you want to go with job one. However, it comes down to how patient is Rick. Because if patience is not a virtue for Rick, he's going to jump the gun and do this. He's still going to make a buttload of money. However, if he just waits a couple more months, this thing is going to climb. Let's say we waited a whole nother year. Let's say 36 months. 2 to the 36? Yeah. That number times 10 to the 10th power. I can't even represent it on my calculator. That's how much money he would be making. That is not even, that's past the trillions mark. So, if he just waits another year, he can do it, which is good. Now Rick, fortunately, is a very patient man. He doesn't seem like it, but being in football those years, he's really gotten patient. He's not as patient as my sister Rochelle. Rochelle Knight is kind of cuckoo, I'm not going to lie. And Rochelle, what are you doing here?
Nice to see you again, brother.